Hello, we are Group 32, and our project is 2HADRAD, a portable life detection radar. 2HADRAD is a handheld system designed to assist search and rescue teams by detecting human presence and estimating the location of individuals in real time. The device identifies indicators of life such as movement, breathing, and body heat using multiple sensing technologies. When these indicators are detected, the system generates visual alerts and positional information, helping responders identify potential human presence and making faster decisions in low visibility environments. This slide shows the core hardware architecture of our system. The sensor subsystem, highlighted in yellow, contains the sensors used to detect indicators of human presence within the device's field of view. At the center of the subsystem is the ESP32 microcontroller, which serves as the main processing unit. The ESP32 collects data from the sensors, manages communication between subsystems, and performs the real-time processing required for the device. The system integrates several sensing technologies, including an infrared thermal sensor, which detects body heat and temperature differences in the environment, an ultra-wideband or UWB module, providing distance measurements that help estimate the relative position of detecting objects when indoors. The system also includes an inertial navigation system, which provides orientation and positioning data. This subsystem integrates an IMU for roll pitch yaw measurements, a barometric sensor for altitude estimation, and GNSS GPS for global positioning information. Finally, an ultrasonic sensor, or USS, is used as a proximity sensor to detect objects that are very close to the device and act as a safety mechanism for the radar. The data from these sensors is transmitted to the ESP32, where it is processed and used to generate information to display to the user.
The sensing component of our system is a 60 gigahertz millimeter wave radar based on the Texas Instruments IWR6843 AOP EVM module. The radar transmits frequency modulated chirp signals and measures the reflections from objects in front of the device. Using onboard digital signal processing, the module analyzes those reflections to detect motion and very small chest displacements caused by breathing and heartbeats. The radar module is powered by a regulated 5-volt line from our power supply board and shares a common ground with the rest of the system. Communication with the ESP32 occurs through UART connections routed through the radar's 60-pin connector. Two UART interfaces are used, a configuration UART, which uses TX and RX lines so that the ESP32 can send configuration commands to the radar firmware, and a separate UART data interface that continuously streams the radar's processed measurement data. The radar firmware packages this processed information into structured binary TLV packets, which are transmitted to the ESP32 through the UART data stream. The ESP32 parses these packets and extracts the parameters we want to display. In our current implementation, the LCD shows heart rate and breathing rate, but the firmware can also output additional information such as target range, motion detection, signal quality metrics, and point cloud detection data, depending on the configuration. In this architecture, the radar performs the sensing and primary signal processing, while the ESP32 handles configuration, packet parsing, and presenting the results to the user through the display.
The user interface subsystem can be seen below in pink. Everything on this PCB is powered by the 3.3 volt rail. First up, we have the red LED, which we have programmed to turn on every time the radar is active to alert the user to stay away from the radar at least 20 to 30 centimeters. Then we designed an audio amplifier. This will alert the user whenever the power system is running and also when a human is detected, and we will probably add some more audio alerts in there. Then we have the LCD, which is the main component of the user interface system. It shows the heat map, the map of the location of the victim, and it also displays a screensaver whenever the system is idle. And then we also designed a 5-way navigational button on this PCB to allow the user to navigate the screen without touching it for environments where it might be wet or the gloves are too heavy. And everything on this board connects to Shannon's board with the ESP32 through screw terminals.
The UWB code resets and initializes the DWM3000 anchor ranging hardware that's on the sensor subsystem PCB board, periodically pulls it for new measurements, and uses the resulting value as live distance from the main unit to the remote tag unit. It rejects clearly invalid ranges and stores the latest good tag distance with a timestamp, and then fuses that UWB tag to main distance with the INS derived distance from the chosen start point, weighing the two based on how closely they agree and smoothing the results so the displayed range is more stable than either source alone. The INS code calibrates accelerometer and gyroscope bias, updates device orientation with the Magic filter, rotates measured acceleration into east and north navigation accesses, and applies several corrections to control drift, low-pass filtering on horizontal acceleration, deadbanding very small acceleration values, damping integrated velocity over time, and clamping maximum velocity. When GPS is valid, it resets the local position to GPS-derived coordinates. Otherwise, it continues dead reckoning and logs the user path and marked victim locations relative to the selected origin. The later thermal rendering block, starting around line 985 here, handles the live thermal screen itself. It throttles updates, retries the MLX 90640 IR frame reads, and smooths successive temperature frames, upsamples the sensor image from 32 by 24 to 64 by 48, converts temperatures into RGB colors for TFT, and only redraws change cells for human detection result. The upsampling is done because the IR only provides a native 32 by 24 frame, which would appear very blocky on the display, so increasing it to 64 by 48 with interpolation does not create new thermal detail. It produces a smoother, easier to read heat map on the screen. The thermal scoring logic computes an average ambient temperature across the frame, finds the hottest pixel, counts pixels that are meaningfully hotter than the background and within a plausible human temperature range, and then updates a persistence-based present score. That score rises when enough hot pixels and sufficient peak temperature suggest a human target and fall otherwise, so detection is less sensitive to single frame noise or brief temperature spikes.
Here's an overview of the code that runs on our ESP32. The opening section defines SPI pins, I2C addresses, and a GPIO expander. Separate blocks handle initialization flags, calibration values, and output variables separately for the thermal camera, the IMU, and the radar. A tile-based menu lets users select thermal, radar, INS, or a placeholder scan. Eventually, scan mode will allow us to access each component in order to corroborate human detection readings and contribute to a confidence score. Each tile is defined by a struct that bundles things like position, dimensions, color, target mode, etc. Each mode has its own screen layout with a top bar containing contextual buttons. Rather than centering text algorithmically, each tile specifies an explicit label X and label Y pixel coordinates. This gives us precise control over where the text appears. The radar uses two UART connections, one for sending configuration commands and another data port for receiving TLV framed packets. The parser extracts breath rate, heart rate, and times out detection if packets stop arriving. The ultrasonic sensor measures distance by triming a trigger echo pulse through the GPIO extender, with results smoothed by a simple exponential filter. Its sole purpose is proximity gating. If the user gets within 25 centimeters, the radar shuts down to avoid near field saturation, and then restarts automatically once they back away. We also have a screensaver feature. After 10 seconds of idle time on the menu, a bitmap image is streamed from program memory to the display. Any touch exits back to the previous screen.
Okay, so we're going to begin this demo with the user interface. So as you can see, we have our screensaver displayed on the LCD screen, and this just appears when the system is idle. So when you tap it, the four options come up, and we have thermal for the infrared sensor, radar, INS, and scan, which runs through all of the systems.
Scan will be interfaced in the future. Currently, we have radar, thermal, and INS working.
So we can jump through these tiles using the 5-way navigational button. As you can see, when we hit radar, the red LED pops up on the user interface board. And this is to indicate to the user that the radar is currently running and to not get too close to it, which the USS also will demonstrate, but we are not including that in this demo video. So we can hit X to go back, and we can select another tile. And there's one more component of the user interface that we're not currently demoing, which is the speaker and amplifier. We are currently troubleshooting those. So here is the thermal map.
So on our IR screen, this is our IR right here, It is detecting yes, and it gives the max temperature that it's detecting and the ambient temperature. So right now I am currently about a meter away, and as I back up, to about 6 feet, which is almost 2 meters, it still detects that I am a human. We have successfully in our trials been able to detect a human as long as they're able to see the skin, like your skin is actually displayed, up to 3.5 meters, which we can demonstrate. So currently Bailey is standing in the frame, and we can see it is still detecting yes as a human. And she is that far away, about 3 meters, 3.5 meters. I'm gonna get out of the frame so you can still see that it says yes, she has been detected. And with the lights off, she is still detected. Thank you, Hector. So Ryan is gonna take over. We're gonna move to radar. And use the button if we go over. Press select. Here you go.
Alright, so I've got the TI IWR 6843 AOP EVM hooked up to the custom breakout board here. That's connected to 5-volt power through the, unfortunately, due to testing, the batteries are low. They have low charge, so in lieu of that 5-volt power supply, we are using a dev board to supply at 5 volts. Because it's currently only outputting 4.7 on the board. However, the 3.3 volts on the power supply board is good, so everything else is being powered by that. So it's running, and we came up to the radar here, and you can see that it shows the USS distance, breathing rate, and heart rate. Now, my heart rate is about 80 to 90, and so you'll see that the heart rate is 87.9 right now. And my breathing rate, even though I'm talking, is like 15.2, which is good because it should be around maybe 12, 17, 18 talking. Yeah, that's right. And so we are fine-tuning the configuration of this, so we should be able to make the algorithm lock on to a heart rate and breathing rate faster. But for now, I think that looks pretty good. All right, so I'm going to back up a little bit, and I'll just read out sort of what the readings are. I'm about a meter away probably, and I'll just keep the camera here, and I'll let you know what it updates to. It may take a minute to lock on here. All right, so it took a little while, but it's now at like 94.9, I believe, which was probably pretty close, 96. And my breathing rate is jumping around now, as is my heart rate, because I'm talking. You sort of need a still position, but that's from 2 meters away.
Now we're going to move on to the INS. So on this main screen, this is before I start and recalibrate the system. Once we do that, we press this little start button at the top. We have mark for mark victims, X to exit the window, and right here is just a simple ASCII map. This is the X demonstrates where we are currently. So if we press start, it will zero it out. As you can see there, the distance is what it's correcting for the drift. Altitude that shows where we're at. The pressure, temperature, how much we're moving, velocity. So we're going to walk. We're on the 3rd floor of the research building currently. We're going to walk to the elevator and go downstairs and demonstrate the altitude difference and the GNSS. Plus we can mark our position on the map for the victim once we enter the elevator. So O on the map is where we started our positioning, which is on the 3rd floor in the research building, and X is where we're moving. Okay, so we are in the elevator currently on the 3rd floor. We're about to be going down. So if you look at the altitude, ALT, it will be changing. You can see the velocity of when how fast we're traveling. So currently we are at negative 43.10 meters altitude, and we're going to be going outdoors to test the GNSS. Okay, so currently, it's really hard to see the screen. We have, if you can see this little light blinking right inside there, that means that it is locked on a satellite. However, on our LCD screen, it is not registering the latitude and longitude, so we will need to update and try to troubleshoot that in the code. But it did register the temperature difference and our altitude difference. So we will work on getting that latitude and longitude to be displaying.